we all be back to normalcy soon. And this challenging scenario will ease out very soon. Okay, so let's start from where we had left in the last session. So for the last 3 sessions, I think now we understand what is an algorithm, why every individual, except irrespective of his, her field of study, must have some knowledge of algorithms. They should understand what algorithm does. And we have also highlighted the terms problems and algorithms. Algorithms are there to solve problems. Today, in fact, in the last session, we have also introduced a little bit of maths, in the sense that we have tried to get some idea about the time required to solve a particular problem. We had discussed the typical problem of a prime number identification, Fibonacci sequence, binary search, bubble sort. Then and then we have also discussed Tower of Hanoi problem, and we have seen that in case of the sorting algorithm we have discussed in the last class, bubble sort, there the time taken is proportional to n square, and whereas in Tower of Hanoi, n is the input size. For Tower of Hanoi, the time taken is 2 to the power n. And we also try to just understand what does it mean, what difference it makes. So today, we will build upon that. In the course of today's deliberations, I'll introduce some basic maths, and some more terminologies which are very, very important. And in the beginning, I just tell you that during the course of discussions, you will also understand which part of algorithm study is a must for students interested in science of computing. Remember, science of computing is one thing, and computer applications is a different ball game altogether. As for example, agriculture science is a huge complex science. Environment science is also a hugely complicated science. For those who are interested in agriculture, they have to understand environment, but they need not have to get into the intricate details inside environment, like environment scientists. So similarly, anybody working on problem solving has to have in-depth knowledge of algorithms. But for students interested in science of computing, have to have absolute details, including the maths of algorithms. And in this perspective, for the students, I tell you one thing: algorithm or science of computing is not a proprietary item of computer science. If some of you are interested to study abroad, say US, Europe, or whatever, good universities, a mechanical engineer can easily think of having masters in computer applications or computer science. Civil engineer can do that. But you have to have at least reasonable depth in mathematics and science of algorithms. Okay. So today let us introduce some basic terms which you may have heard from your school level maths. What is a set? Set is a mathematical term. Set is a group or conglomerate of homogeneous entities. A group of homogeneous entities. Like we can have a set of boys, we can have a set of girls, then we can have a set of students. We can have a set of Bengalis, set of Gujaratis, set of Tamilians. We can have a set of Indians as well. So homogeneity is defined by the property which binds the elements of the group within that set. So what is a set? Set is a group of homogeneous elements. Remember, homogeneity is defined by the inherent characteristics of the set concerned, which defines that set. Now, somebody, I think two classes earlier had asked about soft computing. What is soft computing? It is a huge subject, but one major concept they use is the concept of fuzzy set. What is a fuzzy set? The way we define a conventional set, and we will use that definition only for our discussions. There, if I say set of Indians, yes, having given an element, either he is a member of that set or he is not a member of that set. There is no ambiguity in that. Professor Zadeh, a very famous mathematician, he introduced the concept of fuzzy set. What is a fuzzy set? The membership function, membership within a particular set of an element, there is governed by some probability. As for example, if I define a set of tall persons, now what is the definition of tall? Definition of tall in Germany is different from definition of tall in China. So what is the definition of tall? Similarly, I can have a set of good students. Now, how do you define a good student? Again, there some probability is attached with that. That means the moment I say in a fuzzy set, X is a member of that set, we also have to say member with probability of say 0.4 or 40%, 50%, 60%, like that. And that introduces softness. That introduces softness in there is no hard binding there. So that is known as fuzzy set. In fact, based on fuzzy set, the fuzzy logic has also been defined, and it has a very big follow-up also. But we will not discuss fuzzy set, fuzzy logic. So as you have noted during my classes, I always, before I take the class, I always try to define the boundary conditions within which we are going to talk. That means, what are the ground boundary which we will not talk about and which we will talk about. So we will not consider fuzzy sets and all those. But for those who are interested in soft computing, they have to have some clear knowledge about that. Now, this is a set. Now, what is a function? Function is a mapping between two sets. Suppose we have a set of students. There may be 20 elements, 50 elements, a set of students. Similarly, we can have a set of food items. उसमें बिरयानी हो सकता है, से बिरयानी, चाउमीन, मसाला डोसा, etc., etc. So these two are two different sets, a set of students and the set of food items. And then some students obviously prefer some of the food items, love some of the food items. Some students may prefer some other food items. Function maps the set of students to the set of food items. That means, say, X element X of set A is mapped to elements Y, Z, and W of set B. This mapping is defined by function. This mapping is defined by function. And all these are discussed in details in discrete maths, but just for the sake of a recapitulation. So why do we need this? Now, suppose in this particular problem, I have a set of students, I have a set of food items, and we have gone to a hotel. So we have to order. I need to know how much, how many of which item we have to order. Then this mapping would be required. Then this mapping would be required. So what is a function? Function is mapping between two sets. Function is mapping between two sets. Now let us take a step further. Before that, as a bypass, are you fully aware of what is the difference between an equation and an identity? Ax squared plus bx plus c equal to 0, it is an equation. Whereas a plus b whole square equal to a square plus 2ab plus b square, that is an identity. Why? An identity is valid for all values of its variables, whereas an equation is valid for only some particular values of the variable. I hope you remember that, but if you don't, remember this forever. X squared plus bx plus c equal to 0 is valid for only two values of x, whereas a plus b whole square equal to a square plus 2ab plus b square is valid for all values of a and b. So this is the difference between an equation and an identity. Similarly, what is the difference between a variable and a parameter? Say, when we say y squared equal to 4ax, what is that? It's a parabola. Or x squared plus y squared equal to b square or something like that. So variable defines the nature of a car, and parameter defines one particular instance of that car. Y squared equal to x. Y and x define the nature of the car, whereas a defines a particular variable of the particular instance of the car. So these are basic fundamentals. And another, before I go to our proper subject, another thing I would like you to recapitulate is it's very common that we say that if we want to solve for two variables, we need two equations. Remember, this is an incomplete statement. The equations have to be independent and consistent. You can try with that. Say if we have two equations like y equal to x plus a and 2y equal to 2x plus a, they are same equations. They are not independent, and they have to be consistent. These are some of the basics we may have to refer to during the course of the discussions. Okay, now get down to where we started with. Concept of set and function. Then, what is a polynomial? Polynomial is an expression defined as something like a0 plus a1x plus a2x squared plus a3x cubed and goes up to an x to the power n. That means summation of ai x to the power I equal to 0 to n. That is a polynomial. That is a polynomial. So in the previous class, when we said that the time taken by a bubble sort is n square, n is the size of the input, then n squared is a polynomial. But when we say, and when we found the tower of Hanoi problem requires 2 to the power n steps, 2 to the power n is not a polynomial. And what is the difference between a polynomial and a non-polynomial? For sufficiently large n, the polynomial will increase at a much, much faster rate than a polynomial. Non-polynomial goes on increasing at a very fast rate beyond certain n, to such an extent that this the time taken would be too huge to be infeasible for computation even by the largest machine in the world. So we have polynomial, we have non-polynomial. Now let me try to share one document. In fact, I'm feeling very embarrassed when I want to share this document. Let me try. Can you see that document?
No, sir, it is not visible, sir.
Oh, I have to share it. How do I share it?
Yes, sir. Sir, at the bottom, you see there will be a green icon, share screen. Sir, नीचे sir, mute, unmute. Question answer section, poll, chat.
कुछ नहीं दिखाई दे रहा है. Let me see.
सर Zoom platform दिख रहा है? Zoom platform open कीजिए पहले.
Just let me call my wife. Just a moment. Hey, Sono. Hello. Can you see me? Am I visible?
Yes, sir. Yes, sir. You are visible, sir.
But how do I?
Sir, have you opened the Zoom platform?
Yeah, whatever you have suggested, whatever you have. It is not Zoom.
Sir, at the window screen, are you able to see yourself and Macout logo?
No, I cannot.
Sir, then you
I
have
was
to
seeing.
open with
I
the
was seeing it right now.
bottom taskbar. Bottom taskbar is there, sir. Bottom
I
there
can
will be
see.
some video.
I can see Macout.
Yes, sir. Macout your photo. In that, sir, just you hover the mouse. You just move the mouse at the bottom section.
But I can't see the. I can see. Just a moment. But I can see any of the. Okay.
Sir, you can double click on the screen, sir. You can double click on the screen.
Nothing happened. Oh, let me see.
So I think it is in minimize mode.
But I can't see myself also now.
Yes, sir. Achha, sir, in the screen, can you see the participants list there?
No.
Achha, sir, then you just minimize whatever the thing is open.
Minimized.
Yes, sir. Everything minimized, sir.
So just to see whether I can see the.
Yes, sir. And now, sir, at the taskbar, from the taskbar, you can open that Zoom.
What is the taskbar? That is, I don't know.
Taskbar, sir, bottom, there is a window button.
And I can't see
Google
myself
Chrome
also.
Button.
Can you see myself?
Yes, sir, you have not. Yes, sir, you are visible. But yours, yeah, your interface is not visible for your side, sir. From your side, it is not visible. So,
that's fine.
sir, are you able to see the time at your computer?
Yes.
Just left side of that, you can find there will be many icons, sir. Just beside left. at the bottom.
Okay, I'll do it later on. I'll try to get it done later on. Let's continue further
Okay,
with what I've been saying.
okay, sir.
Hello. I'll get it back later on. So I found some problem in sharing the screen. We'll do that later on. So what we have been saying, just consider a particular example. Suppose we have two sets. I have now defined the sets and the and we have defined the function as mapping between two sets. Can you tell me how can I get my picture back?
Sir, for that I have told that you can see the time in your computer at the right bottom
टाइम तो
corner.
पूरा नीचे है.
हाँ सर, पूरा नीचे आता है सर. सिमिलरली यू कैन मूव फॉरवर्ड लेफ्ट साइड. टाइम के बगल में सर आपको लेफ्ट की तरफ जाना है.
एक मिनट.
जहाँ पे टाइम है सिस्टम का, उसी के लेफ्ट में जाना है. तो नीचे एक टास्क बार रहता है, तो वहाँ पे सर वेरियस आइकन्स मिलेंगे, जैसे गूगल क्रोम.
हाँ, गूगल क्रोम हो तो है.
हाँ सर, उसके बगल में सर एक जूम टाइप का होगा, एक ब्लू स्क्रीन वीडियो कैमरा जैसा.
ओके, इज इट दिस?
हाँ, क्लिक कीजिए सर.
बट नथिंग इज कमिंग.
सर दो स्क्रीन होगा, उसको आप क्लिक करने से निकलेगा. आप वहाँ पे माउस को रख के देखिए, वो आइकन जो नीचे है.
ठीक है, चलो तो थोड़ा देर बाद देखेंगे. ओके. So now suppose I have two sets and a function which maps between these two sets. Let's take a typical example, because I'm trying to share with you the actually I'm feeling very uncomfortable in not seeing myself.
Sir, you can send me the PPT. I can show it from my side in my mail.
That is again a problem. But okay, that I can do.
Sir, from our side it is okay, sir. You are visible, audible, all the things are working.
No, but you are not seeing my PPT. This share is not working. But where do I share? That is the.
Sir, one thing you can do, you just rejoin once again. It will take 1 minute only.
Okay, so I get out and rejoin?
Yes, sir. Yes, sir. Yes, sir.
Just a moment. Just a moment.
শেয়ার করতে গেলে তোমাকে ওইটাতে যেতে হবে. এটাই সোজাসুজি পাবে না. তোমার ইয়েটা কোথায়? মিট
কিছুই দেখতে পাচ্ছি না. ওটা কিন্তু
ব্যাক করে এই তো, এটা বোধহয় তোমার. বুঝতে পারছি না, আবার ঢুকবে?
বললো বেরিয়ে এসে আবার
সেটাই ভালো.
আচ্ছা, এইটুকু তো হবে, এইটুকু বেরিয়ে এলে হবে না?
Host has stopped your video. Join new meeting.
না, বেরিয়ে আসো, একদম বেরিয়ে আসো.
আমার মেলেও থাকবো না বলছো? হ্যাঁ, মেল থেকে যেটা করলাম. জয়েন নিউ মিটিং দিয়ে দি.
নিউ মিটিং দিয়ে তো লাভ নেই, বেরিয়ে আসো. এটাও বেরিয়ে আসো.
Yes, sir. You just restart the thing. The
restart.
link.
আচ্ছা.
Yes, sir. You can just
new
restart
meeting.
the link.
New meeting.
Yes, sir. No, sir. You can just rejoin. After logout. That you close all the application. You close all the application.
Close all the applications. কি হলো এটা? বন্ধ কি করে অ্যাপ্লিকেশনটা? লিভ মিটিং করে দিই তাহলে.
এটা কোথাও উদা হয়ে গেছিল, কোথাও কিছু একটা প্রেস করে দিয়েছি একেবারে। হ্যাঁ লেগে গেল, মানে আমরা জানি না তো, মানে একেবারে নবিশ। সো এবার আমার ছবি কি? হ্যালো।
Yes, sir. You are visible and audible, sir.
Okay, let me see. Let me আগে শেয়ার দেবো না একটা বার?
So first you
Share
start the
screen.
application that you want to share.
Share
Sir.
screen.
Click on the share screen.
এবার এটা
Press on the first option, screen.
share. এই
Yes, sir. Yes, sir. It is displaying now. So you can now switch to the content that you want to show, sir.
but how can I see myself that?
So it will be a small video at top right corner.
কোথায়?
You are visible, sir. You are visible at the side top. You
And
just
the
open
screen
the
is,
content.
and
Yes,
the
sir. Yes,
content.
sir. Screen is visible. Yes, sir.
Okay, okay, fine.
Monotonical. Yes. Sir. Set
Thank you. Okay, first of all, once again, I'm feeling very embarrassed with my handwriting. I do not know. So believe me, my handwriting is not that bad. But thanks to this technology, I've been using this, tab or whatever you call it. So it will take some more time to get adjusted. Okay. So I have defined the terms set and function already. Then another term, monotonically increasing function. What is that? For f of n is function n. So we have given a picture like this. If a function is like this, this means what? For any n such that n1 is less than equal to n2, then f of n1 will be less than f of n2. Simply speaking, it will grow in non-decreasing order. Why non-decreasing order? They may be same also. So why I have introduced this monotonically increasing function term? Because if for any algorithm, for any problem, we define fn as the time taken to compute that algorithm for input size n. We expect n to be, we expect fn to be expanding in non-decreasing order as n increases. That means as the input size increases, the time taken to solve the problem should also increase. This is a simple, naive, straightforward expectation, irrespective of the problem and irrespective of the algorithm. So this is monotonically increasing function. The examples we have given, that bubble sort n square, as n increases, it increases. Tower of Hanoi, and 2 to the power again, n increases means the time taken will also increase. Then I am defining big O notation, which any computer science application or IT student must be familiar with by this time. But every one of us should be familiar with this term, because this is a widely used notation to define the computing time of an algorithm. Let me read out the statement, then I'll explain physically. Big O of Gn is, G is a function of n, is a set of Fn such that there exists positive constants C and N0 such that 0 less than equal to fn less than equal to c of gn for all n greater than equal to n0. So this is a very, seems to be very difficult statement. So let's, for physical interpretation, let's come down to this picture. What it says, once we get, somehow we compute the time to be taken by an algorithm to solve a problem, we expect it to be in the form of a polynomial or non-polynomial with the help of an expression with n as variable, where fn is that variable. Now, bgo of gn defines an upper bound. It is known as asymptotic upper bound of that function. Again, let us get back to our previous example, the sorting. We knew that the computing time taken would be n square, which is a polynomial. And if we plot fn versus n, and if fn is n square, we'll have a monotonically increasing function. We can always define some positive constant c so that this monotonically increasing function will asymptotically reach that c of n square. Again, what does it mean? If the function is n square, we can call the complexity as big O of n square. Complexity as big O of n square. Similarly, big O is the upper bound. Big omega is known as the lower bound. Big omega is known as the lower bound. So again, this is the asymptotic lower bound where up to which this fn goes. So big O is the upper bound, big omega is the lower bound. By this definition, if the fn is n square, can we call it big O of n cube? Can we call it big O of n to the power 4? Of course, yes, because those are in the upper bound. But generally, we always try to mention the tightest upper bound. The tightest upper bound. So, n square we call big O of n square. But formally, tight upper bound is defined by small o, and tight lower bound is defined by small omega. If the upper bound and the lower bound are same, that means big O and big omega are same, we call it big theta. So these are the technical terms. I would suggest you to read any book on algorithm, but be very careful. Some books do not represent it properly. I would suggest you to read Corman for this definition. Now, a few anecdotes with this. For many problems, we may require more than one algorithm to solve the problem. More than one algorithm to solve the problem. So, and each algorithm will have its own complexity. So it is at least intuitively obvious that big O of n square plus big O of n square will be same as big O of n square, because big O of n square essentially is a polynomial in n square, a polynomial with n square as the highest degree and same. So addition will remain same. So if we have an algorithm with several parts, summation of the complexities of those parts will lead to the complexity of the algorithm as a whole. And this is how we define this. So I just wanted to introduce these terms, even though I believe computer science IT students, computer application students, they are fully aware of that. But you should be very clear about what is meant by big O of n or big O of Gn. And remember, technically speaking, big O of Gn, big O is basically a set of Gs. But so long as we know what big O means, it's fine. I wanted to introduce this so that now, henceforth, during my deliberations, I can use the term big O, because without using the term big O, I was finding difficulty in referring to any algorithm. Okay, so in this context, we have already discussed the Tower of Hanoi problem, how to move a set of disks to another set, that is 2 to the power n, of the order of 2 to the power n, and just compute manually. If n equal to, say, 4, n squared is 16, 2 to the power n is also 16. If n equal to 5, n squared is 25, 2 to the power 5 is 32. Just see, when you compare between a polynomial and a non-polynomial or exponential, after certain n, this term increases at a much faster rate than a polynomial. And there is the problem. Why do you need a computer? Generally, we need a computer only when n is very large. For small n, we do not need a computer. So when n is very large and the algorithm complexity is not polynomial in nature, the time taken would be so much that it will not be feasible for any computer, whatever be its speed and memory, and to solve it in a feasible amount of time. So we have to be careful in dealing with algorithms whose complexity is not polynomial in nature. There are many problems with real-life applications which come under this category. Down the line, we'll definitely discuss some of these algorithms. But for the moment, you can think of one very common problem, say chessboard problem. You cannot, it has been proved mathematically, just like Tower of Hanoi problem, that you cannot design an algorithm computable in polynomial time to solve a chessboard problem. So what do you do about it? Then, in that case, you make some restrictions. It's a chessboard problem. We make a restriction, say, of 10 look ahead, 15 look ahead, something like that. And up to that, it will work. We say that. And that's the reason why, so far, we could not design an algorithm for chessboard problem which can beat anyone in the world. Some top grandmasters just beat computer programs on chess very easily. Okay, so now we have to again understand that for any particular problem, we can have many ways to solve the problem. And many ways means we can have many algorithms to solve the problem. As for example, for sorting, There are probably hundreds of ways to solve the problem. Every problem, every algorithm will have its own complexity. And as we know, efficacy of any particular problem also depend on the instance, on the applicability of that algorithm. We have seen in the last class, while sorting a problem, if we use the bubble sort the way we defined, used in the last class, worst case, it should take n square. But if it is already sorted, it will take only n. So which algorithm to be applied when? That depends on the nature of the problem, the data set. Another very common example is, say we want to multiply two matrices of size n by n. What would be the complexity? 2n by n matrices to be multiplied. So in the final matrix, that will also be n by n. So in the final matrix of n by n, to compute each element there, how many multiplications will be required? N, and n square such element. So that would be n cube. So computational complexity of multiplying to n by n matrices would be of the order of n cube. Now suppose in some cases where the n by n matrix has most of the elements as 0. Most of the elements as 0. In many examples, we require that. So can we do some smart thing so that the complexity goes down from n cube to some lower value? So you can also appreciate that in such cases, complexity of the algorithm in some cases may be brought down by using appropriate data structures. That means how do we store the data will have some impact on the complexity of the algorithm. We'll discuss at least something about data structures and all those in the next session. And then we'll be free to discuss algorithms in further details. But for today's talk, to the concluding part, let's get down to, again, the topics we had started with. What was that? Set and function. Let us take a typical example. We have a set of, say, cricket players, a set of cricket players, 100, 150. Think of auction in IPL. You may have noted that. Set of cricket players. On the other side, we have a set of positions in the cricket, like batsman, bowler, wicket keeper, specialized slip fielder, like that. Now, we have to choose 11 players such that at least one of them would be a wicket keeper, say 2, 3, 4 bowlers, some batsmen like that, And remember the way we have introduced this set, 2 sets, we know which players can bat, which players can bowl, which players can bat and bowl both, which player can, okay. Through that mapping, we can do that. Through that mapping, we can represent that. Now, through a function. Now, out of these can you imagine the possibilities Yes, Rajiv, some question? Somebody wanted to raise a question? Yes. Rajiv, go ahead. Unmute yourself. Unmute yourself. Okay. So at least intuitively, can you imagine how many combinations you have to handle? How many combinations? It will be a very complex combinatorial problem. It will be a very complex combinatorial problem. And obviously, with complexity of non-polynomial in nature. Now, when we do it manually, they do it in IPL auction and all those, they have another constraints, like each player has to be purchased at some cost and total budget is fixed. You cannot get the best one. So, but how do we manually? Because we have some idea about some players. We have some idea about some players, and then we decide, say we'll take 5 bowlers, 5 batsmen and 1 wicket keeper. Someone may decide we'll go for 5 bowlers and 6 batsmen, one of which whom could also be a wicket keeper, something like that. So many things we have in the back of our mind while choosing the proper selection. But as we know, if we leave the selection process to the computer, we have to design an algorithm to do the job on our behalf. And the computer cannot judge. Computer cannot make any decision of its own. So it has to handle all possible combinations. It has to handle all possible combinations. And any algorithm which takes care of all feasible cases and then come to a solution is known as exhaustive enumeration. Exhaustive enumeration. But this is a very naive approach. This is a very naive approach. You have to have some smart ideas to avoid, at least to minimize to some extent, this exhaustive enumeration to solve the problem. In fact, the entire discipline of artificial intelligence is concentrated on this particular aspect only. How do you plan, design algorithms smartly so that you need not have to go for exhaustive enumeration? Then, Prem, can I take 5 minutes?
Yes, sir.
Just 5 minutes. This is exhaustive enumeration, and that is why artificial intelligence is so important nowadays, because most of the social and jobs which human beings were supposed to do is being downloaded to the machine. So they have to be tailored accordingly, but exhaustive enumeration is not acceptable. So based on domain knowledge, based on the situation, how can we do the best? Then there's another aspect also. Like, take another example. Forget about another aspect. Say, suppose you have some symptoms. You go to a doctor. doctor will hear about the symptoms and give you some medicine. This is nothing but an optimality problem. Most of the computer science, in fact, practically all computer applications deal with optimization. We have some objective functions, some boundary conditions, and we want the optimal solution. And in many cases, these are extremely hard. When we say extremely hard, I mean their complexity is not polynomial. What is their complexity? We'll talk later on. These are known as decision, or these are known as optimization problems. That means, having given a problem, having given the constraints, you have to optimize the resources. Having the problem, in the previous case, I have a set of players, I have the constraints of budget. What is the optimal solution? This is known as a decision problem. Think of a corollary of that problem. For some reason, suppose you feel that this could be the solution. Now, if somehow you can anticipate some solution and then try whether that solution is optimal or not, that would be a much simpler problem. Decision problem would be a very complex problem. We have to do the entire optimization and all those. On the other hand, you can somehow, if you can have some solution in your mind, and the problem now to check whether this solution is optimal or not, okay, this is known as decision problem. And the solution of a decision problem will always be yes or no. The question would be, suppose there is a solution. Is it optimal? The answer should be yes or no. So these are known as decision problems. So in many cases, optimization problems are very complex, but the decision problem corresponding to that optimization problem is much simpler. But again, they are not guaranteed to give you the desired effect. And finally, another kind of demarcation is deterministic and heuristic. These I will discuss in details in the next session as well, because these will be the basic platforms for our discussion on algorithms. Deterministic means which gives you the exact optimal solution. Heuristic means you know very well that this is non-polynomial. So the decision problem will take, the optimization problem will take infinite amount of time. So can I have something which gives me a satisfiable solution? I know that this is not optimal, but I also know how far from optimality my solution is. But the beauty is I can compute it in much less amount of time. Those are known as heuristic algorithms. So these terms you should remember very well. This optimization problems, decision problems, optimality and satisfiability, exhaustive enumeration, deterministic, heuristic. Today I have already introduced the term big O. And for those who are interested in science of computing, I would suggest you to read Corman, the book by Corman, and what is known as Master's Theorem, which helps you in solving recurrence relations to find the complexity of an algorithm. Just for applications, we may not be interested in science, we may be interested in the knowledge, in the result only. But for those who are interested in science, who wants to make a career in theory of computer science, or for whatever reason you are interested, you may be interested in the science itself, then read Coleman and Master's theorem. Okay, I think I have to close here now, no, Prem?
Yes, sir. We have another engagement, sir.
You have another meeting, but a couple of students raised their hands, but they did not respond.
Yes, sir. I have called their names. No issue, sir. We will take the questions via mail also. Participants, if you have any question, yes,
you can take the course then in the next session, because we have to
yes,
switch
sir.
off. So in the next class,
Yes, sir. We can take the questions in the
I am
next class
expecting
also.
at least some questions on today's class, because now we are gradually getting into the depth. So, so in the next session, we will start with these questions and then go ahead. Because what I always follow is the question may come from anybody, but the discussion should be in front of everybody, so that everybody understand, also participates in the deliberations. Okay. So you can take the questions, note down in the next session, because we don't have time today.
Yes, sir. Participant,
Okay?
you can send your question in your mail. In the mail,
You
and
collate all those.
we can forward it to sir.
No, you keep it with yourself. I do not need. You keep it with you, and say from next session onwards, say first 5 to 7 minutes, we will spend on deliberations on those questions.